Hello, my chemistry friends. I am going to go over a little bit today what we've done in class with identifying, predicting products, and balancing chemical reactions. And in particular, we're looking at composition, decomposition, and single replacement. Hang in there, we can do this. First off, composition reactions. We want to pretend like we're matchmakers. So we have, in this case, A plus B, or whatever we're working with, and we're going to match them up to be one, and so it'll be AB together. One thing, here's some common examples, and I want to show you a couple things within these examples. First of all, I want you to see that oxygen, for example, is O2, and nitrogen here is N2, and hydrogen's H2. And the reason why they have those twos there is because they're diatomic molecules. So when those are by themselves, remember the enes and the gens, when they're by themselves, they want to be with diatomic. However, when they're in a compound, so when we put Mg and O together, notice I don't bring the two over. The reason why I don't bring the two over is just because when you start a new relationship, you don't want to bring in baggage into the relationship. That would be a recipe for disaster. So we put Mg and O together and we look at the charges. Mg would have a 2+ charge, oxygen would have a 2- charge, and when we crisscross, they're going to cancel out. So that's how we got the MgO. And then we go to balance our equation. The second one here, we just smush Al and O together. Al has a 3+ charge, oxygen has a 2- charge, so then when we crisscross, we get Al2O3. Again, it had nothing to do with the fact that there happened to be a diatomic over here. We have a new compound and we look at it like a new compound, just like you would look at it as like a new relationship. We have H2 and N2 together, and I want to point this out because sometimes we forget, but even though H is with N, H is a +1 charge and N being a 3- charge. So we sometimes think of a hydrogen as a gas, or it is a gas many times, but we think of it as a nonmetal. So therefore we think, oh, well, it can't have a plus charge. Well, it certainly can. It has a plus and a 3-. So then that's how this 3 got here. And then we balance our equation. So how do we actually predict these products of a composition reaction? Well, we actually, we just put the two reactants together. So let's say, for example, I have calcium and I have nitrogen. And first off, I want to think about that nitrogen is actually, it's a gen, so it's going to be a diatomic. So I have the nitrogen. Notice I put a little reminder over here. The gens and the enes are the diatomic molecules, or you can always remember, have no fear of ice cold root beer. Anyway, so I come over here and I find the products. So I'm going to smush those two together. They carry no baggage into their new relationship. Calcium has a +2 charge. Nitrogen has a 3- charge. So I crisscross to find my subscripts there. So I have Ca3N2. N2 on my product side, N2 on my reactant side. So I'm good on my nitrogens. I have 3 calciums. I need 3 calciums on my reactant side. So I add a 3 in front of it. Another example could be iron and chlorine. So I think about this, iron and chlorine. Oh, I got an E and I have a diatomic. So I have to put my 2 there for my diatomic. I'm going to smush them together. Now they're a couple. And sometimes it's hard to think, okay, so what's my charge on iron? Well, your charge on iron is you look in the back of your periodic table at your reference sheet, and you see that iron is oftentimes a 2+ or a 3+. So what we were going to do is take the lowest of the two. And so we're going to assume it's a 2+, and chlorine's a 1-, so we crisscross, so we bring our 2 here. This 2 came from the 2 charge on iron, not from the 2 because chlorine was diatomic over here. So please clarify that and please make sure you understand that. Now, this equation is now balanced. Let's go to decomp. So composition, we were making matches, and unfortunately decomposition, everybody breaks up in decomposition. So we start here. Here's some examples of decomposition reactions, and this one's a little bit different because with this decomp, we have 1, 2, 3, we have 3. So it's very hard to consider how they actually break apart. And I'm going to show you a trick to that in just a minute. Sometimes you have a nice clean break where you have just two elements within your reactant that's going to break up. And so we can just break them apart. But let me show you the tricks. So when we have a polyatomic here, how does this actually break up? And there's some tricks to that. So let's take a look, and I'm going to move my screen myself over real quick. If I can grab it. All right. Anyway, let's take a look here. I'm going to move this. Yeah. I'll move me right here. Okay. You'll see this little table I have here at the bottom. And this table is the carbonates, chlorate, hydroxide, and acid. So it gives us an indication of if we have one of those, what does it break into? So let me go through a couple of examples here. Let's start with sodium carbonate. So we've got sodium carbonate, and unfortunately, sodium carbonate is going to break up. So we need to break it up. We don't just break it up into sodium and carbonate. It just doesn't work that way because carbonate is a polyatomic ion. But carbonates, if we read over here, break into carbon dioxide and then a blank O. That blank is for a reserve for the metal there. So we're going to break up into carbon dioxide. And then our metal here is sodium. So we're going to do Na, and then we have O. Now, Na is a plus charge, O is a 2 minus, so we have Na2O. So basically, sodium carbonate broke up into carbon dioxide and sodium oxide. So now we have to check to see if we're balanced. So we have 2 sodiums here, 2 sodiums here, 1 carbon, and then we have oxygen in 2 places on the product side. We have 2 plus 1 more, so we have 3 oxygens and 3 oxygens. So this equation is actually balanced already, so we don't have to add anything else. What if we break up something that's a little bit of a cleaner breakup? So we have FeO. So we're going to break up iron 2 oxide, and we just basically fall apart here. So we break it up into iron and oxygen. But the one thing we have to be considerate of is we have to think, okay, do we have a diatomic? And yes, we do. In this case, we have oxygen. So oxygen's by itself. That's why it has to be 2. So we look at that and we say, okay, we have 2 oxygens here. Now we have 2 oxygens on our reactant side, but now we have 2 irons. So let's get 2 irons on our product side. The biggest thing is when you practice is look at your carbonates, chlorates, hydroxides, and acids. Some people forget what a hydroxide is. Remember, it's OH, and it's a 1 minus. So if you see something like lithium hydroxide, or if you see calcium hydroxide, those are some examples of hydroxide. So don't freak out if you see something you're like, oh, it's not going to be a clean break where you just break into 2 separate elements. There's some rules behind that, and here are those rules. All right, now let's take a look at single replacement reactions. And single replacement reactions, I'm going to move my face down here again. So we have a single element, and then we have a compound, and then we have a compound and a single element. What you need to see here, though, is, for example, here's our single, and that single, whether it be a metal or a non-metal, if it's a metal, it can only knock out another metal. If it's a non-metal, it can only knock out another non-metal. This must be a metal since it's knocking out B. So A knocks out B, hangs out with C, and B is left hanging. Now we have to decide if that's even possible. So let's look at some single replacement reactions. So we have silver nitrate and nickel. So nickel is our single, and nickel is a metal. So we look to see, can it knock out silver? So we use something called our activity series, which is this document right here. And you guys should have a document with the activity series on there. So we find silver within our activity series, and we find nickel. And since nickel is above silver, it can knock out silver because it's more reactive than silver. But silver cannot knock out nickel. Well, nickel is the one that's by itself, so nickel can in fact knock out silver, become nickel nitrate, and then leave silver hanging. Now the second one here, my single is chlorine. So therefore my chlorine is a nonmetal, so I'm comparing it to bromine, which is the other nonmetal. So I look over here at my activity series nonmetals, and I see chlorine and I see bromine. And chlorine needs to knock out bromine. Chlorine is above bromine, it's more reactive, so therefore chlorine can in fact knock out bromine. But look where it's knocking it out. So now chlorine's going to go and hang out with aluminum and leave bromine hanging by itself. Now look at this one. We have magnesium as our singleton. So magnesium's a metal, so we're going to look at it against calcium. So here's magnesium, here's calcium. Magnesium cannot knock out calcium because magnesium has less activity than calcium does. So therefore, what we write is no reaction. And Rxn is a common way in chemistry to write reaction. So magnesium cannot knock out calcium. So we basically, if we would put magnesium with calcium chloride, we'd make a fun mixture and be like, that's it, nothing else is happening. So let's try a few examples here. Let's try magnesium and let's try nitric acid because you think, gosh, there it is, that hydrogen again behaving like a metal. So our singleton is magnesium, and magnesium is behaving like a metal, and hydrogen is going to be behaving like a metal. So we look at our activity series and we find hydrogen and we find magnesium. And magnesium is higher active than hydrogen, so it can knock out that hydrogen. So therefore, I'm going to have magnesium nitrate. Nitrate is a 1 minus. Magnesium is a 2 plus, so I'm going to put a 2 on the outside of my NO3. And I'm going to leave hydrogen gas hanging. But remember, it's hydrogen, so we need a diatomic here. Now we want to balance. We have 2 hydrogens and 2 nitrates. And if we put a 2 in front of our nitric acid, then we balance it. That 2 is terrible. Let me see. There we go. That's a little better. Let's try another one. Let's try sodium bromide, NaBr, and let's see what it does with iodine. So iodine here is a nonmetal. So between Na and Br is also a nonmetal. So we need to see if iodine can in fact knock out bromine. So we look at our activity series and we see iodine, we see bromine, and iodine is below bromine on the level of activity, so iodine cannot knock out bromine. So therefore, this is called no reaction. And that's all you have to do. You don't have to try to balance, you don't have to predict theoretical products, nothing. You can just say no reaction. So these are the first types of reactions: composition, decomposition, and single replacement. And we're going to work on the rest tomorrow, but let's take a little bit at a time and just practice those things that just practice predicting the products and be sure to always balance. We always want to make sure we balance those equations. All right, take care, guys. Bye-bye.